Hey folks, welcome back. So our lesson for this week is a little bit different. You've got your regular front and back class notes, but then there's also an additional page with some diagrams that you're going to be using as kind of a worksheet while you're working. So make sure that you've got that out where you can actually draw on it. This is not going to be something where you can do it on the computer screen very easily. So you want to make sure that you're actually able to pencil on that. So print that out, make sure that you've got it available for this one. What we're going to be doing today is we're going to be learning how to find distance. So we want to be able to find the distance to a star. Why does that matter? Well, first of all, we want to know how far away the aliens might be so we know whether we can communicate with them or not. But also, later on, we're going to learn that when I look at how bright the star is, that's telling me how much energy it's putting out. But remember, if it's a long way away, it can seem dim, even though it's actually really bright. So if I see a star out there and it seems really bright, okay, is it really bright, which means that the planet would need to be a long way from the star, or is it just close? So one of the first things I've got to figure out is how far away is that actual star from Earth? And you'll be able to use this technique with anything once we're done. So let's get started. This is going to be Tool 6, Finding Distance. Now you'll notice the titles here are chosen very carefully. Let's say you're working on your final project and you realize you need to find the distance to something. Well, now all you got to do is you go back through your tool book, through all of your class notes, and you just look for the one that says finding distance. And it will show you every step of the way how to find the distance. It'll build it up so that you know what you're doing from that. So it's a good way to review. So each one of these tools will give you a specific task that if you need to go back and figure it out, you just find that one task and you're ready to go. All right. Now, the stars that are closer to us seem to move, and that's a phenomenon called parallax. So I want you to try this experiment. So just on the screen here, take your finger and hold it at arm's length so that it's in the middle of the words here, so that you've got the nearer stars seem to move as your background there. All right. I want you to close just your left eye. Now close just your right eye. Did your finger seem to move? Like for me, it moves kind of from one side of the word to the other. All right. Now, take your finger and put it right up against your nose. Now close your left eye and then close your right eye. Where did your finger seem to move more? When it was far away or when it was close? Well, for me, when it's up close, it actually goes from one side of the screen to the other. So this phenomenon is called parallax. What's happening is your left eye is, when your left eye is looking this way, it sees the finger over here. When your right eye is looking at it, it sees the finger over here. The farther away that is, though, the less of a shift that you're going to see. But when they're up close, now the angle is very big. And so it seems like it moves back and forth. This is how you're able to see in 3D. So you actually are only seeing two 2D pictures. But because they're slightly offset from each other, your brain is able to put those together and make 3D. And this is actually the secret behind 3D movies, VR, things like that. We're showing two offset pictures. Your brain then is programmed to turn that into where it looks 3D to you, but you don't actually see in 3D. It's your brain that's creating that illusion. But the key thing to think about, though, is the closer the object is to you, the more it's going to seem to shift due to parallax. So let's see how we can do this with stars. So here's the sun, and this is the orbit of the Earth. So the Earth takes a year to go around the sun. So we've got these background stars here that are so far away they don't seem to move. And then there's this foreground star, this near star, that I want to figure out the distance to. We'll call that distance d. So when we're talking about the distance, we're talking about the distance from the sun to that star. All right. So what I do is I take a picture of the star in January. It doesn't matter which month, as long as they're 6 months apart, but let's say January. So from in the picture, then, this star will appear to be right here in the middle of all the rest of these stars. Can you see how that would work? Because remember, the picture looks flat to me. I'm not going to see it in 3D, so it's going to look like it's just pasted right over here. 6 months later, in July, I'll take another picture. Now the star seems to be over here. So it'll seem to have shifted, just like your finger seemed to shift. You didn't actually move your finger. It's just you were looking at it from a different angle. Well, here we're looking at it from the entire width of the Earth's orbit. So the radius of that is 1 astronomical unit. 1 AU is the distance from the Earth to the sun. It's about 150 million kilometers or 93 million miles, something like that. So that's enough to get a shift here. So if I want D, I now have a right triangle. Now, if you remember back to high school and you talked about the the sine and cosine and tangent and all of that, don't panic. You don't actually need to know that because this angle is going to be so small that there's a small angle approximation we can do to it. But this angle right here, because I need a triangle, I need a right triangle. So that's called the parallax angle. The total amount here is called the parallax shift. The parallax angle, the shift is this whole part right here. So I'm going to draw that. So that's the shift. The parallax angle is half of that shift. So just from here to here. Okay. So the parallax angle then if I know this distance, if I know my baseline here, if I know this and I know this angle, I can figure out that third side that's there. So let's use this technique and see how we can figure out the distances to stars. And we're going to build it piece by piece. Now, we're going to do this a little differently because what I want you to do is I want you to pause the video and I want you to actually do the first page of the class notes exercise. So it's going to be referring to this picture right here. Okay? So when it says, for example, that use a straight edge in figure 1, draw a line from Earth's position in January to determine where it's going to be. That's exactly what we did before. You're going to take up the straight edge, you're going to draw that line, and you're going to see that the star is going to appear here. All right? Pause the video, work out just this first page. Once you've done that, restart. We're going to go over that, restart the video, and then we'll pick it up with the second page. Again, guys, it's not about getting the answer. It's about the technique. And so if you're just blasting on through going, oh, I'm just going to watch the video and just let it go while I'm doing other things, then it's really not going to help you much. And you're going to be pretty lost by the time you get through it. It's the act of doing it that's going to help you. All right? Pause the video. Let me know as soon as you finish that first page, come on back, and then we're going to go over that. Okay. Hopefully you actually paused the video. So I'm going to switch screens here, and I'm going to go to the PDF here. So let's do this together. So it says, using a straight edge on figure 1, draw a line from Earth's position in January through the nearby star to show where it would apparently be with respect to the distant stars. Okay, that's a lot of words to just say you want to do something that looks like this. And obviously I don't have a straight edge, so I'm doing the best I can, right? Then it says, using the same method, determine which distant star the nearby star will appear close to, as seen from Earth in July. Now, if you didn't quite understand what the instructions are and you're looking at this and you're going, oh, now I see what he's doing, pause the video, go back and fix it, and then come back, all right? And that goes true for all the rest of this explanation here. Okay, so this one's going to look like this. So we have it, get it all the way down there. So we have a diagram similar to what we showed in the PowerPoint just a little while ago. Okay, so the angle between the two lines that you just drew is the apparent motion of the star as seen from Earth. But the parallax angle used is half of that. So it says draw a line from the sun to the nearby star and then extend it to the distant star. So what we mean, draw it from the sun to the nearby star all the way out here. Because this is the distance that I'm trying to find, right? So the parallax angle, then it says, is the line from the sun to the star and to one of the lines on either side. All right, what that really means is this. Or alternatively, you could do this. Those are the same angles because we've just split it in half, basically. And you may say, well, wait a minute, didn't we do it over here before? Yeah, and if you remember geometry, this is called an alternate interior angle, but this angle and this angle are actually the same. And this angle and this angle are actually the same. So it actually doesn't matter which one you're measuring with that. All right, so this is our parallax angle. All right. So now it says draw another nearby star approximately twice the distance from Earth as the other star. So just to clean things up a little bit, I'm going to erase this, but you don't need to erase it on yours. It's fine. You're not going to be turning this in. We'll do this in red. So this is going to be our other nearby star. Okay. So for the first one, we had an angle that looked like this. All right. Now, okay, maybe closer to Now we're going to do it in red. Now I've got an angle that looks like this. Can you see that? Okay, so this is my, and then it's on the same line, so this is my parallax angle P2. So how do the angles compare? So if this angle is parallax angle 1, you can see that that's a bigger angle than P2. And that's what we're looking for there. So when the object is farther away, this is the important part. When the object is farther away, it's got a smaller shift. That's why there doesn't seem, by the way, that's why there doesn't seem to be a shift for these background stars. They're so far away, they actually are shifting, but the shift is too small for us to measure. With our current equipment and our current technique, from the ground, we can measure out about 100 stars away. It's called a parsec. We'll talk about that in a second. From space, we can do maybe 200 parsecs away, 200 stars over. So beyond that, the shift is just too small for us to be able to see. So then the question says, will a distant star, an even more distant star than our red star here, will it have a larger or smaller parallax? What do you think? So it's more distant. It's actually going to have a smaller angle. Think about your finger. The closer it was, the bigger the shift we saw, and the farther away it is, the smaller the shift that we're going to see. All right. So as the distance goes up, the angle goes down. So it says, is that directly proportional or inversely proportional? Think about what we introduced when we were talking about telescopes. If I've got this situation, is that directly proportional or is that inversely proportional? Since they're opposite, that's inversely proportional. So what that tells me is that as the distance and the parallax angle have to be in opposite places. And there's going to be some constant here. We'll eventually learn that that constant is 1 for now. But as the distance goes up, the parallax angle goes down. That's what inversely proportional is. And you see that we have actually figured out the equation already. Without really having to do any math, that's what science is. All right? Okay, so if you're not sure about that, go back and review it. Make sure that go over your worksheet and make sure that you've got a good handle on it, because you're going to want to understand that before we talk. This is how it looks in space. Now we're going to talk about how it looks like from the ground for how we actually use it. All right, so at this point, I want you to pause the video and do this worksheet. Okay, so you're doing page 2 here, the how we use it part right here. Now, just to give you a little bit of an explanation, this is the same part of the sky taken over the course of 12 months. And you'll notice that most of the stars stay in the same position. However, one of the stars seems to move relative to the background stars. That's our nearby star that's shifting slowly back and forth. So in the first part, we're going to ask you to circle that and so that you can identify that. Once you've done that, you're going to come back to this page here, and then you're going to mark the extremes of where it went. So, for example, if you found that it went from up here all the way down to here on our different pictures, you're going to plot those 2 points. So the moving star is not in this picture right here. You've got to draw it. And you're going to see that it's separate. Use the background stars to figure out where to plot that picture. And then the last thing that we're going to have you do, if you look at this scale bar right here, and hold it up to the camera so you can see. So if you look at that scale bar right here, the length of that bar is 0.25 arc seconds. I need to explain what an arc second is. So you're probably familiar with degrees. How many degrees are in a circle? 360 degrees in a circle, okay? So all the way around the sky would be 360 degrees. Now, if I take 1 degree and I divide it into 60 pieces, each one of those little pieces, and 1 degree is about the width of my finger, held at arm's length on the sky. So if I divide that into 60 pieces, one of those little pieces is called an arc minute. Now, if I take one of those arc minutes and I divide it into 60 pieces, that's an arc second. And so you see, an arc second is a tiny, tiny, tiny sliver of the sky. And here we're talking about 1/4, 0.25 of an arc second is that bar. So these shifts we're talking about are really tiny. You are never going to see them with your naked eye. You're only going to be able to see them with a telescope from that. So the length of that bar is 0.25. So when you've plotted your 2 stars, you may say, okay, I think it's 5 bars across, 5 of those black bars, 5 times 0.25 is going to be 1.25. So that means that it shifted by 1.25 arc seconds. Make sense? If not, review it and play it a couple of times and see if you get it. All right. So once you've figured that out, then remember that that's the parallax shift. The parallax angle is only half of that. And so then you can use that parallax formula that we just derived, and it's sitting down here at the bottom of your page, and you can figure out the distance to this star that's moving. Okay? Pause the video. That's a lot of instructions. Pause the video and see what you can do. This is really helpful to do it with a group from that. So if you get a chance to do it in a group, that's going to be the best way. Otherwise, just pop back into live help and I'll help you. Pause the video. Do it now. Okay, you got it done? All right, so let's take a look at it. So we want to locate and circle the nearby star in each one of these. Now this is going to zoom back out as soon as I try to write. So we're looking to see which star is moving. Do you see that here we've got a difference? So one of those two stars must be our nearby star. So take a look. So that one still seems to be in the same spot. So this seems to be the same spot. So this must be our moving star. Do you see that? So we're going to circle that right there. So that's our moving star. And therefore, this must be the moving star, which means probably this is the moving star. So you're going to do that in all of these pictures. So you see what happened was, let's see, you know what? I'm going to get rid of this piece because that is interfering. So let's do that. There. Now you should be able to see that a little bit better. So you see what happened was it started, went to an extreme, and now it's turned around and it's coming back. So this must be my nearby star, and then here it is right here, and then right here, and then here. Do you see how I'm doing this? I'm comparing it. And so now that must be it, and that must be it, and there. Now it's over here, and now it's over here. Okay. So that's my star that's moving. So it says determine which 2 months is at its extreme position. So where are the turnaround points? So if we look at it, it looks like right here is one of them. So we're going to say March. And then you see it starts to move back over this way. And it reaches an extreme somewhere over in here, right around September. See that? Which, not coincidentally, is 6 months away. So March and September then are going to be my 2 lines. So I want to plot it where it appears in this month and in this month. So let me bring up that page. So we're going to bring up this one right here. And so we're going to plot on here where it was. So our first one ended up to be right about here, maybe. And then our next one ended up to be right about here. And hopefully you can be more precise than I'm being right now. Okay, so that's the parallax shift. So the next thing you have to figure out is, it says indicate the length of the parallax angle. So the parallax angle is going to be half of that. So that either side, since they should be the same, and you probably want to be a little more precise than I'm doing, but about half of that is going to be the parallax angle. So now we want to measure how many of these scale bars is that. And it looks to me like that might be 2 of those scale bars. It might be 1.5, but you estimate based on your particular drawing because you can do it a lot better than I can with this pen right here. So for now, let's suppose it's 2. If it's 1.5, you do it your way. And so if it's 2, then that means that the parallax angle here must be 0.5 arc seconds. Now, if you decided it was 1.5, or if you decided it was 1/2 of those, so then that would be, you would probably have gotten 0.375. So you do you, whatever works out best for you, but you should get somewhere in between 0.375 and 0.5 arc seconds with that. All right. So now we come down here to our formula because now we want details. We want to actually get a number, so we have to actually do some math. And so the distance is 1 over 0.5. So pull out your calculator. Now there's 2 ways you can do this. The most straightforward way, you just do 1 divided by 0.5, and I get 2, which kind of makes sense if you think about it. 0.5 is a half. 1 over a half is just going to flip it. It's going to be 2. The other thing you might look for is on some calculators, and I don't know if I do on this one or not. Yeah, actually on this calculator, I have a 1 over x button. On your calculator, it might be x to the minus 1. You can think of that as being your parallax button. So all I need to do then, I could put in 0.5, hit that 1 button, and look at that, magic. It tells me that it's 2. So this star must be 2 parsecs away. And we're going to talk about where that comes from when we go back to the PowerPoint here in just a second. But a parsec is a unit of distance, not time. So when Han Solo said that the Millennium Falcon made the Kessel Run in under 12 parsecs, no, that was George Lucas not really understanding what a parsec was. So it is a unit of distance. And in our part of the galaxy, each star is about 1 parsec away from the other stars around it. So you can kind of think of this as being 2 stars away from us. So this particular star that we're looking at here is 2 stars over from that. All right. So if you're not clear on this, go through it, see if it makes some sense, but then come by live help and let me explain it to you. All right, we're going to shift back over to the PowerPoint now. Okay, so this is how it would look like from Earth. So we would have a picture here, and then the star would shift. So that amount right there, that's the parallax shift. That's what you saw in the picture that you made for the worksheet. Half of that angle is going to be the parallax angle. So P is the parallax angle, which is half of that shift. As we pointed out, it's measured in arc seconds. A good rule of thumb for formulas, for equations, and this is your very first equation that you've had to work with. A good rule of thumb is make sure that you know what each of these symbols means and know what its units are. Because that's the hard part, is figuring out, okay, what D is this and what P is this, because we're going to run into a whole bunch of different Ds and a whole bunch of different Ps. So you're going to need to know for this particular equation, P is the parallax angle measured in arc seconds, and D is the distance to the star measured in parsecs. Now, a lot of times in Smart Sparrow, they're going to want you to give your answer in light years, and that's fine. 1 parsec is 3.26 light years. So all you got to do is take the number of parsecs you measured, multiply it by 3.26, and you're golden. So for example, our example here was 2 parsecs away. 2 times 3.26. Go ahead and do it. What do you get? I get 6.52 light years. See if that's what you get as well. So a light year is also a unit of distance, not time. It's how far light travels in 1 year. So that means if we were to send a message to the aliens around this star, it would take 6.5 years, 6.52 years, for the message to even reach them. And then for them to send a reply would take another 6.5 years. So even at a minimum, if they instantly reply back to us, it's a 12-year round trip, 13-year round trip. All right, let's do a little concept quiz here. What I want you to do is I want you to pause the video, pull out your calculators, and let's see if you can calculate the distance in light years to each of these stars. Look very carefully. Do you see this as light years? This is where a lot of students mess up in the lab and in the assessment. Read what Smart Sparrow is asking for. If it asks for it in parsecs, give the answer in parsecs. If it asks for it in light years, you better multiply by 3.26 so that you give it the right answer, because for example, 6.52 is not the same number as 2, and vice versa. All right, so pause the video, see if you can work out what each one of these are, and then let's come back and let's check your work. Did you get it all done? Don't just let it keep going. Make sure that you got it. All right, so we've got 1/4. Now, 1 over 1/4 just means flip it. So you know the answer is going to be 4. But let's test it. So if we do 1 divided by 4, I get 0.25. And then 1 divided by 0.25 is 4. So this is 4 parsecs away. But that's not light years, is it? What do I need to do to get it to light years? Multiply by 3.26. So times 3.26, I get 13.04 light years. Make sense? All right, let's do the next one. So it's 0.326 arc seconds. It's not inches. That little double mark doesn't mean inches. It means arc seconds. So don't think that you're going to be converting from inches to anything. It's arc seconds. Okay, so I'll do 1 divided by 0.326. And I get 3.07 arc seconds. Notice, see all those numbers right there? Remember, you don't need all those numbers. If you write down all of those numbers, you're doing it wrong. You need to only keep 3 significant digits. So I look at the 4th significant digit. In my case, that's a 7. So that rounds up that 3rd significant digit, and I've got 3.07. That's parsecs. So what do I need to do to convert to light years? Multiply by 3.26. And I get 10. So it's 10 light years away. All right, let's do another one. So this one is 2 arc seconds away. That's actually crazy close, but whatever. 1 divided by 2 is going to be 0.5 arc seconds. It's going to be 0.5 parsecs, sorry, times 3.26. So this one is 1.63 light years away. So if it was half a parsec away, we know it's closer to us than the nearest star, right? Because each star is about a parsec away from each other. So it turns out this is about halfway between us and the next star. All right, and the last one. So 1 divided by 0.652, I get 1.53 parsecs. Notice that the 3 doesn't, the 1.533 doesn't round up because it's less than 5. So I've got 1.53 parsecs, and then I'm going to multiply by 3.26, and I get 5 light years. Make sense? If you're not sure, go through it. If you're still having trouble, come back to live help, and we'll go through it. You must learn how to do this. All right, so in summary then, the apparent motion of the object is going to, with respect to a different background, will shift as your observer changes. And so that's that parallax going back and forth and back and forth. The parallax angle is half of that shift there. And then I'm going to start showing you all the tools, the equations that you're going to need to be keeping up with from here on out. And this is the first one that actually shows up in your equation sheet. The distance is 1 divided by p, the parallax. And then most of the time, you're going to have to multiply by 3.26. Now that means if I wanted to go ahead and put it in my formula that way, I could do d equals 1 over p times 3.26. Well, that's just 3.26 over p. So if you want to remember that that's going to be, that light years is 3.26 over p, you're welcome to do that, but I don't actually recommend that because this form, the original form, is so much easier to use. And then you just look at the answer that they're wanting and decide. If I want it in parsecs, I'm done. If I want it in light years, I'll multiply by 3.26. It's easy. And then you're ready to go. Then the last thing we want to say is we're limited to about 200 parsecs because after that, shift is just too small to measure. But that's okay, because as we said in the very first class, we're really interested in finding these aliens that are close to us. And most of the planets we've been studying have actually been within 200 parsecs of us. So all of the stars that you're going to be looking at in your final project when you're looking for your alien world are going to be within 200 parsecs. All right, so that's it. So we're going to get some practice with that. So download your finding distance practice worksheet. It'll give you some problems. Now here, we're actually looking for details. So you're going to do the math with this one. And then there is one relationship question where I'm wanting you to circle the correct response for that. So download that, work it out, scan it, and upload it to the website. Okay, so now you know how to find the distance to any object in space. And then it really doesn't even matter what it is. You can find things anywhere in the solar system. You can find things out to the farthest reaches of space, up to about 200 parsecs. So that's our limit. We can only use this technique up to 200 parsecs. If you ever want to find things that are further out than that, take 112, astronomy 112, and that's actually, I'll be teaching a whole bunch of different techniques for finding things all the way out to the edge of the universe from that. So if you're interested in that, there's lots more that you can learn in astronomy. For now, we'll focus on aliens because, hey, aliens are cool. We'll see you next time.